Today we're going to talk about oscillations, and in short we're going to basically put everything in A-level physics in the realm of oscillations into this video. Mind you that this is based off the Cambridge International Examinations Board, but it should be similar for most of the A-level exams boards. Anyways, so let's get started. What is an oscillation? An object is oscillating when it moves back and forth repeatedly on either side of an equilibrium position. This is really simple. There are two types of oscillations. There are free oscillations and forced oscillations. So free oscillations vibrate at something called the natural frequency after initial disturbance. You don't have to push the object again and again in order to make it vibrate or oscillate because it has a natural frequency of the body that's gonna just follow. Forced oscillations do not vibrate at the natural frequency. The vibrations of another body are transmitted to the body. For instance, if you keep pushing a child on a swing, making it faster than its natural frequency, that's a forced oscillation. So we can observe frequencies that are smaller than 5 Hz, which means less than 5 oscillations per second. This is a very simple diagram of an oscillation. The object will accelerate towards the center. It's going to travel at the highest speed at the center, and then it's going to start decreasing, and then it's going to stop, and then it's going to accelerate again and again and again. This is obviously because of gravity, which is like this, and it has a component in this direction, and it's this direction that pulls it towards the center. This force that allows it to accelerate, and this would obviously change directions when you go to the other side. So oscillations can be actually described sinusoidally with a graph. It's said to be a sinusoidal motion because the shape of the oscillation is a sine curve if you decide to graph the displacement to the time of the object, and the displacement being from the original position of the object. For instance, this would be the original position, displacement would be this distance. So the XO, which is over here, that's the amplitude, that's the maximum displacement. The period, which is, you can see either one, this is like a cosine curve sort of thing, or you can just look at one sine curve. The period is the time for one complete oscillation. The frequency is the number of oscillations per second. Just do T equals 1 over frequency. Phase is the point that an oscillating point has reached within the complete cycle of an oscillation. So for instance, let's say this is one full cycle, right, over here, and let's say this one is like around here. At this point, it has reached actually 1/4 of the total period, and so that means it's either, you can say it's like 1/4 times 2, because the full cycle will be 2 pi, which gives us 1/2 pi. You can also represent this using 90 degrees. It's the same thing, and you have to assume that the full cycle is 360 degrees. So we go into a hugely important subsection of oscillations, which is about simple harmonic motion. And now we have simple harmonic motion in basically most of the vibrations that we see in real life. Example, if you pluck a string on an instrument, it's also in an alternating current. The electrons move back and forth with simple harmonic motion. It's in when you speak, the particles oscillate like this. It's in, just every single solid ever. It's in an actual pendulum. Yeah. So what is simple harmonic motion? Well, you have 3 requirements. Firstly, you need a mass that will oscillate. Secondly, you need a position where the mass is in equilibrium, which means that there is no resultant force on it. Then thirdly, you need a restoring force that returns the mass to its original position. This has to be directly proportional to the displacement, x. What does that mean? Well, let's say this is the equilibrium position, and that means that this is going to be x equals 0, displacement equals 0. This right here is going to be XO, that's the amplitude, that's the maximum displacement. What happens over here is that when this is displaced to the maximum displacement, it will start accelerating more and more until this position. At this position, because it's accelerated so far, it will be at the highest velocity. But because it's at the equilibrium position, it's at the bottommost position, there's no resultant force on it. And then when it reaches this through momentum, it's going to start decelerating because the resultant force is going to be like this. So it's accelerating in this direction, which means it's decelerating, stops a bit, and then it accelerates like this again. So what is the most important thing here is that actually the displacement is the opposite direction as the acceleration. Let's say this is a positive and this is negative. Let's say that the displacement is somewhere positive here. Then that means that the acceleration is going to be towards the negative side. Let's say the displacement is at a negative part. Then the acceleration is going to be toward the positive side. And you also have to know that the acceleration is directly proportional to the displacement, which means that the more you are displaced from the equilibrium position, the higher the magnitude of acceleration. So let's take a look at the graphical representations of simple harmonic motion. So let's assume that, let's look at the displacement and the time graph. Let's assume that the body starts at x equals 0. Then you're going to have a sort of sine curve. Now, let's say you decide to differentiate this once. And differentiating the displacement with respect to time will obviously give you the velocity. So if you differentiate a sine curve, you're going to get a cosine curve. And so you get a cosine curve here, which is very self-explanatory. And let's say you decide to get the acceleration. You differentiate it again. And if you differentiate a cosine curve, you get a negative sine curve. You see a negative sine curve over here. It's this one, but flipped. So that makes sense in terms of calculus, but it also makes sense when you think about it more like logically and practically. When the displacement is 0, we've noted that it has the maximum velocity, which you can see here. We've also noted that at the equilibrium position, it is in equilibrium, there's no force on it, which means that the acceleration has to be 0, which we see over here. Each point correlates to the feature of the position that the body is in. For instance, when the body is at maximum displacement, we know that the velocity is momentarily going to be 0 because at the maximum displacement, the oscillation stops for a while, changes direction, and then starts to oscillate again. So we see coincidentally that the velocity is 0 here, very momentarily. But we also know that at displacement equals maximum, the acceleration also has to be the maximum. However, it has to be in the opposite direction as the displacement. And we can say that this is the maximum as well, but it's the negative of the displacement. So these graphs can really help put things into perspective. So then let's introduce angular velocity into oscillation. You probably know that angular velocity is basically the amount in angles that the some sort of body traveling in circular motion travels per second. For instance, if this body oscillates like this and it travels maybe this much in a second, that's 90 degrees per second, you can say that that is 1/2 pi radians per second. How am I going to introduce this into oscillations? Well, let's say you take a look at this oscillating body, but then you take a look at it from this side, so you're just basically seeing a line. Imagine that. Then as this travels at a constant angular velocity, it's going to travel much faster over here. To you, it's going to look like that. And then when it goes to the top, even though it's like traveling at the same speed, for you, this is just going to be a small section in comparison to this, but this is going to take a long time to go through. So it's going to look like it's traveling very slowly here. It's also going to look like it stops momentarily here. That's exactly like simple harmonic motion. You're going to see this ball travel quickly up, slow down, stop, and then go down quickly, and then slow down, stop. So this means that we can take a look at an object in circular motion, take the angular velocity, and use it at oscillations as well. A complete oscillation is 360, which is also 2 pi radians per oscillation. And so we obviously know that frequency is 1/t, the period. And we now know that the angular velocity is the frequency times the entire cycle of the oscillation. For instance, if the frequency is 1, that means that there is 1 oscillation per second. So the angular velocity would be 2 pi per second. If the hertz, it was like 100 hertz, then it would be 200 pi radians per second, if that makes sense. So our equation is omega equals 2 pi f. And obviously you can substitute t into f and make whatever equation you want from there. So then let's start explaining why the simple harmonic motion can be expressed in a sine graph. So we know that the simple harmonic motion that you see here, this is a body, let's say you displace it to one side and you let go and it oscillates back and forth, is going to be x equals xo, maximum displacement, sine omega t. That's an equation. And if you really think about it, because we know that simple harmonic motion is sinusoidal, it travels in a sine curve, like so. Over here we have pi, and like we have to represent this not in pi, but in radians actually. And then over here we have the displacement, and you can put this as meters or cm or whatever you want. Now this sine curve is going to be determined by the amplitude of the sine curve, which is the maximum displacement, and it's also going to be the radian of like the angle of whatever point you're in. However, this is not an angle. We don't have the angle when we just look at an oscillation. So in order to get the angle, we just multiply these two together. You have the angular velocity, which is equal to 2 pi f, and then you times that by t. And that is actually 2 pi times 1 over period times the time. So let's say you're like 1/4 of the way into the period. That means you're going to be at this part. And so if you do that, and if you cancel it out, it's going to get 1/4 times 2 pi, which is going to give you 1 out of 2 pi radians. And this value of radians, if you put it in here, you can see the exact position of the body. And so that's why we use this equation. If you want a more detailed explanation of why these equations exist, I highly suggest you click on this video that I'm going to link, where I really go in depth about the equations of simple harmonic motion. But this is what it is. We can also state that x equals to the, amplitude cosine omega t if it's just starting at a different position. So this one is for when the body starts at x equals 0. However, if the body is starting out at a maximum position, then it's going to be cosine. And I hope that makes sense to you. We have this equation about the acceleration of the oscillation. And we see that a equals to negative omega squared x. First thing to note is that a and x have a negative sign between them. This applies to the simple harmonic motion quality that acceleration is in the opposite direction as the displacement. In addition, we see that these two are proportional to each other, which also applies to the simple harmonic motion property that acceleration is directly proportional to the displacement from the equilibrium position. The constant of proportionality is negative omega squared. If you want a detailed explanation of why that is, you can go and check out my video on it again. The stiffer the spring, the higher the force for a given displacement. And I think that's pretty self-explanatory. It requires more force to be extended, and therefore it will contract with higher force for a given displacement. And hence the higher the acceleration, hence the frequency would be higher for a stiffer spring. So this equation, acceleration equals negative omega squared x, is a definition of simple harmonic motion. This equation must be fulfilled for a body to be in simple harmonic motion. You need a negative sign, you need proportional a and x, and you need a constant of proportionality for a body to be in simple harmonic motion. Let's read this out here. A body executes simple harmonic motion if its acceleration is directly proportional to its displacement, and in the opposite direction to its displacement. If you decided to graph the acceleration of a body in simple harmonic motion to the displacement, you would get this, because it is, directly proportional. You would get a straight line. It's going to be negative like this. It's going to pass through the origin, and that's what it's going to be like. So what we can see here is that the gradient is independent of the amplitude, right? And therefore, because the gradient is omega squared, and omega basically relates to the frequency and the period of the oscillation also has to be independent from the amplitude. So we have this very handy equation over here, x equals xo sine omega t. So let's just write that down once. Using this, we can get so many different equations. We can differentiate it once to get the velocity of the object at any time. And if you differentiated this, then you would get omega xo cosine omega t. If you differentiate it again, you would get acceleration, which would give you omega squared xo cosine, negative, and then this would turn into sine omega t. So there you go. You have the three equations, and they're all from differentiation. However, we can change that. So we just now had v equaled to omega xo cosine omega t, right? But we can change it into this, because ultimately this would still be a cosine curve. So you can have something like that. And this is just going to be VO. So the maximum velocity is going to be extreme value if you want to put it there as well. And this obviously works because these time together to get the angle in radians for you. So yeah, you could also express it in this way. And we have this equation as well. But before that, we also can prove why VO equals to this. That's V equals omega xo cosine omega t. So when does a certain body in simple harmonic motion have the maximum velocity? Well, it has it when it is at the equilibrium position, when x equals to 0. So that means that t has to be 0, because at x equals 0, t equals 0 if you say that the starting position of the object is at equilibrium position. So cosine 0 equals to 1, which means that VO equals to WXO, because this becomes 1. And so you can basically substitute this. So you can prove it in two ways. And then we have this equation as well, which I'm not going to prove. It's not in the syllabus at all, but basically we have that velocity is also equal to plus minus omega times the maximum displacement squared minus the displacement of that object at that time squared. Let's say that you want to get the maximum velocity. That means that the equilibrium position will be there, so this is going to be 0. And so VO is going to be equal to plus minus omega times XO. So you can actually prove it in 3 ways. But there you go. So you have these two equations. So we have a short summary here of all of the equations that you've just learned. Omega is 2 pi f. The displacement can be represented like this. And you can also get this equation, A equals negative omega squared x. You can also get this equation. You can also get this equation. And these two both pertain to the velocity. These two will both give you the fact that the maximum velocity equals to the omega times the maximum displacement. However, you can go ahead and memorize all of these if you want to, but I think that you don't have to, because a huge majority of these can be just found through simple derivations. For instance, you don't have to memorize this at all because it's so easy to derive. You don't have to memorize this if you already understand the definition of omega. I would suggest that you do learn this one and this one. This can also be kind of derived pretty easily, I believe. But yeah, these two you would have to memorize because I think they take a little bit more work in terms of derivation. And this is the definition of simple harmonic motion. I think that it's also good to know that. So now let's talk about the energy changes that happen during simple harmonic motion. During simple harmonic motion, there is a constant interchange of kinetic energy and potential energy. Potential energy can be of all sorts. Remember that pendulum that was swinging back and forth? That would have a gravitational potential energy exchange. This one right here would have an elastic potential energy exchange. Really depends on the system. And then for kinetic energy, obviously, it's just kinetic energy for anything that moves. So yeah, we know that at the equilibrium position, there's no resultant force on it. However, there is maximum velocity, which means that the kinetic energy has to be the maximum and the potential energy has to be 0 because there's no equilibrium, there's no force on it at the equilibrium. Provided that the oscillations are undamped, and we're going to go into that later, but it means that they basically keep going and they don't lose energy due to like friction or whatever, the total energy in the system remains constant. So let's say the blue represents potential energy. And so it's going to oscillate up and down with the changing position. Kinetic energy is also going to oscillate up and down with the changing position, but if you add them together, you will get a straight line, meaning that energy is conserved. So let's take a look at this very handy graph. It's a graph of energy to the displacement. This is the positive maximum displacement. This is displacement equals 0, aka the equilibrium position. This is a negative maximum displacement. The blue represents potential and the red represents kinetic energy. Kinetic energy is the maximum when displacement is at 0. So we can see that. And actually, I drew this pretty inaccurately because this actually should be touching the total energy line. The kinetic energy is going to make up the entirety of the energy of the body, and the potential energy is going to be 0 at this time. However, at any point on the graph where there is a maximum displacement, the body will stop momentarily, which means kinetic energy will be 0 and potential energy will be the maximum. It will be the total energy. And there also is a certain point on each part of the graph where the potential energy equals the kinetic energy as well. And actually this point is going to be around like 70% of the maximum displacement. It's not going to be 50% because you have to know that EK equals to 1/2 mv squared. And you also have the energy of the potential thing, and this is going to differ for any sort of system that you use, but it's most likely going to be constant with the displacement. So that means that if you equate these together, you're going to get some sort of equation, and then you have to like prove in some sort of way. But the overall thing is that usually this point is going to be around 70% of it. It's going to be more than half. And at any point of the graph, the total energy has the same value, and it's just the sum of the two types of energies. And this is provided that there is no damping, which means that energy is not lost, and it's a perfectly oiled, no friction type of system, which is, in real life, that's impossible. In real life, you would have damping. So let's get into damping. Damping happens because of friction most of the time. For example, with air or fluid friction, or with springs or strings or the equipment when it's not well maintained. The oscillations decrease as the friction transfers energy away from the mechanical system to the surroundings, and they are damped, and usually it's made into heat. So when they are damped, the oscillations will go down like this in terms of the amplitude, because the amplitude basically shows how much energy you have. So the amplitude of the damped oscillations decay exponentially with time. The big amplitude has a high speed, which means it has more energy, and therefore there's more energy lost because frequency would remain the same. And smaller amplitudes would have lower speed, right? And that means it has less energy lost because frequency remains the same. So basically, you are traveling at a lower speed. That's why the decay is exponential. Let's introduce another component, which is resonance. Resonance is when an oscillating system is forced to vibrate at the same rate as its natural frequency, and when its amplitude of vibration increases rapidly due to its maximum frequency because of it. So remember we differentiated forced and free oscillations last time? Well, imagine if you had a forced oscillation, which means there's a system that keeps transferring energy to it, but it does so at the same rate as the natural frequency. So the oscillation, the amplitude, is going to be increasing extremely rapidly. That's resonance. If the driving frequency is not quite the same as the natural frequency, the oscillations will still increase, just not to such a great extent, because there's going to be time where the oscillations are going to oppose the driving frequency, and then energy is going to be lost. The energy is absorbed from the driver to the system. And so for a body in resonance, its natural frequency is equal to the frequency of the driver, its amplitude is at a maximum, and it absorbs the greatest possible energy from the driver. So let's say you have the driving frequency, and the driving frequency basically gives energy to a certain system. We measure the amplitude of the system. You see that at the natural frequency of the system, when the driving frequency equals the natural frequency, the amplitude is going to be the maximum, so that's the point on the graph where resonance happens. This happens with, things like bridges. I'm pretty sure everybody has heard the story of this random bridge. I think it's in England that there were a lot of wind, and then the bridge like resonated with the wind, and then it wasn't supposed to, but the entire bridge started oscillating like to the extreme, so they had to shut it down and then do some renovations on it. Let's see how damping and resonance interacts. We can use damping to reduce the damaging effects of resonance, as we've seen with the bridge example. So as the degree of damping increases, the amplitude of the oscillations in resonance will also actually decrease. The resonance peak broadens and the resonance frequency also decreases. So for the driving frequency, you have no damping, which means the amplitude is going to be extremely high and the peak is going to be much narrower. There's going to be light damping, and then heavy damping. And you can see that actually the maximum, the resonance frequency actually decreases the more damping you put on it. In addition, the peak is also going to broaden. For instance, if you let go of this door, it must not, go back way too slowly. That's too much damping. Nor must it have no damping and then swing back and forth again and again. It has to go back and just close, but not too slowly, and also not swinging back and forth. And so that's when we use something called critical damping. Critical damping is the minimum amount of damping required to return an oscillating body to its equilibrium position without oscillating. But it's the minimum amount, which means that it's not too much damping, so it won't take a very long time. So here are the different types of damping. Let's say that this is underdamped. So it keeps oscillating back and forth, and if your door oscillates like this, it'll be very annoying. There is critically damped, which means it's the lowest amount of damping possible to return it without swinging back and forth, right? And there's overdamped, which is too much damping, and it takes way longer, and it is annoying. So yeah, underdamping results in unwanted oscillations. Overdamping results in a slower return to equilibrium position. And let's round off with uses of resonance. So resonance is in musical instruments, it's in microwave cooking. The water molecules are made to resonate at the same frequency as the waves, the microwaves that are coming out, and that's because the microwaves are at the natural frequency of the water molecules. Magnetic resonance imaging, MRIs, also make use of resonance, it's in the name, and radio tuning circuiting, where the radio waves are also going to make particles resonate and therefore transmit the information that we need. So, that's about it for our fast summary of oscillations. Obviously, there's much more to this chapter than a very quick summary, but I think this should cover enough for quite a bit of the exam. If you want to go into more in-depth, then I highly suggest you check out the videos I have made on each of the parts of oscillations in A-level physics. I think will help with a deeper understanding. I hope this was helpful to you, and if you want more videos on A-level physics, do check out the rest of my channel. Thank you for watching.